Welcome back to another episode of Dominic Does DIY. As always, if you haven't subscribed, go ahead and click the subscribe button and click the bell icon. If you find it interesting, if you can share to help out, that would be great. I was going to make something this week, but Amazon got me. They sent me a CAN bus shield for a Pi instead of what I wanted, so that'll be next week's thing. In today's episode, we will actually look at a boost circuit since it was requested on the last video to look at a boost buck and a cuck. And so I just went ahead and started with the boost circuit, and we will take a look at that and see how it is designed. We will take a look at the general overview and how it basically operates, and then after understanding that, we'll look at the details on how a boost IC works internally and come to understand how we can actually design for one. So let's get into it and see what we got going on. The basic idea of a boost circuit is you have a lower voltage and need a higher voltage. To do this, we exchange current for voltage. Basic idea is power in equals power out. Quick back of the napkin math for determining what you need is most boosts are about 85% efficient. Thus, if you are looking for a 12 volt at 500 milliamp output from a 3.7 volt source, it's just 12 volts times 0.5 amps, gives you 6 watts divided by 80% efficiency, gives you 7.5 watts on the input. Divide that by 3.6 volts, and it gives you 2.08 amps from the source. So we need to make sure that our supply can support 3.7 volts at 2 amps if we want to have a 12 volt, 500 milliamp output. So first, let's understand the overall operation of a boost in real basics and go up from there. A boost at a core is turning an inductor into a voltage source in series with the main source, giving us a V out equal to V source plus the voltage across the inductor. So how does it do this? Well, here M1, this is what we refer to as the switching FET. And when we short the switching FET, we actually cause the inductor to be shorted to ground, which allows us to charge the inductor. And as we know from engineering school, right, the voltage across the inductor is equal to L di dt. Now, when we open the FET, we know that current cannot instantly change in an inductor, so current remains flowing in the same direction, but the polarity of the inductor flips, putting the inductor in series with the main voltage source, and thus the voltage at the V out equals V source plus V inductor minus the diode drop right here. The diode is required to allow the output capacitors to run the load during the time the FET is on and charging the inductor. So when the FET is on, obviously the source cannot supply the load, so it is these capacitors that actually feed the system with power, and the inductor is there to ensure that those capacitors can do their job. Let's say that diode was not there. Then what would happen? As soon as the switching FET would close and short to ground, well, all the energy that was stored up in those capacitors would also be dissipated across M1, and then we would have no power for the load. So the diode is a critical component for this design. So since we understand now how boost basically works, how is it that we can make this work? Well, the basic principle is to find a way to be able to switch this switching FET in order to maintain an output voltage and size the caps large enough to be able to handle the load when the inductor is charging. So we want to be able to close the FET and short the inductor to ground when we have sufficient energy on the caps to supply the load. And then when those capacitors lose energy, we want to then open up the switching FET in order that those caps can be recharged by the source and the inductor. There are a ton of different boost controllers out there that you can just buy that basically handle all of this. But in this simulation, obviously we're going to take a look more at the hardware and understand. And then once we see how this works, the basic premise is the same across any of the controllers that you may look at. So you just take this and then you got to look at the data sheet, and they'll give you their formulas, which are basically the formulas I'll go through in order that you can do what you need to do. So the first things that are required in order for the controller and in my simulation to work is a feedback loop. We need some way of knowing what the output voltage is. So we have this R1 and R7 here, and this feedback voltage that we will then use to kind of understand what voltage our output is at, so we can make a variable boost. And this is also used in many other controllers. So in the data sheet, you'll just want to look what their V feedback voltage is. Sometimes it's 1.2, sometimes 1.25. But when you see that voltage, that's basically what you're shooting for, depending on your output voltage. So when we're talking about controllers, that's about it. This circuit that you see right here, the inductor, the diode, the FET, the feedback resistors, and the capacitors, these are all external components to the controller. The controller basically takes the feedback voltage in and then will spit out a control signal to turn the FET on and off. If you're running a low power system, a lot of the controllers, they'll have the FET built in, and usually you're limited to like 1 or 2 amps based on the silicone of the part. So if you want a large boost converter, then you're going to need a boost controller that has an external FET rather than an internal FET. So what's that controller chip actually doing on the inside? Basically this, right? We've got 2 comparators. And so you can see there that we have our feedback voltage coming into the first comparator, and we're comparing it against some reference voltage, right? Remember I said that the chip usually has a feedback voltage. This is what it's doing. It's going into a comparator and it's checking that feedback voltage to make a signal. When is the voltage at the voltage level that you want, and when does it drop below it? Basically, when do we have enough energy and when have we lost energy, in order that we can take some sort of action to turn the FET on or off. Then the next thing it does is, with that information, it then goes into a wrap comparator. And so when you see a controller IC, it basically says that we are working at this frequency, this PWM or PFM mode. But basically they've got a ramp circuit in there, some sort of oscillator that's giving some sort of signal of the switching frequency that they want as the overall switching frequency. So in this one, most of the controllers I see that I've worked with, it's anywhere between 250K to 500K is about their switching frequency. So that's all I did here, is I just used a voltage source, created a pulse, and then just generated a ramp signal with it. Did it at about 500 kilohertz. So what's going to happen? Well, as the ramp system goes up and down, right, it's going then to react to the comparator output of the VREF and the V feedback, and using that, it'll determine when does the FET turn on and when does the FET turn off. I'll show you some simulations and you can see it working. It might not click right now, but once we see the signals, it'll make perfect sense what's going on. So now, how do we design it? Again, if you got a controller that you're working with, look in there. They'll have a write-up on exactly what to do. But basically, all the formulas are the same, or there's some derivative of this. So the first thing we need to do is lay out some basic parameters of how we want this thing to work. Right? We need to basically design and say how we want this thing to operate. So you can see here, I've chosen a VN, a minimum of 3 to 3.6 is my nominal. 4.2 max, this may sound familiar, it's just a standard issue single cell lithium battery. My V out, I was going with a 12 volt output. I'm just saying, hey, I want a 1 amp output. I just pick a number, that's for your design, right? My output voltage ripple, which will go in to calculate the capacitor, is 50 millivolts. Again, this depends on your circuit. The more voltage ripple that you can handle, the smaller your output caps will be. So then the operating frequency, like I said, since we're designing it, you can make it anything you want. I've seen 250 to 500. I just went with 500 here. And then you can find some controllers out there that even work up to 1 megahertz. The thing with the frequency is the lower the frequency, the bigger your inductor needs to be. So if you want a smaller inductor, then you want a higher frequency. But also, the higher your frequency that goes, the less current that you can push, right? So it's like a balancing act, but really you want to try to keep as high a frequency as you can in order to keep that inductor on your design smaller, right? Because that's what ultimately matters. It's board space and cost. So the smaller the inductor, the cheaper the board. And then finally, we have to design in some sort of efficiency number just to do some calculations, right? And like I said, most controllers out there are about 85. So when I'm doing my stuff here, just so I don't get my hopes up too much, I just always go with a design calc of 80% efficiency, and then usually I can come out better. Usually I can get around like 85, 90, depending on what I'm working at. So now that we got all our inputs done, now we have to calculate our outputs. You can see here, I've got a bunch of formulas on the right side here. And like I said, these are the standard issue formulas. They may vary slightly depending on the controller you get, but ultimately they'll be this. And so you can see here, I just went through and then put these formulas into the Excel sheet. And some things just to note, right? When you calculate your inductor here, you can see it uses a delta inductor current, like you're changing inductor current. But to get the delta I, right, you need your inductor. So it's kind of a circular logic there, right? You got formula 1 that says, hey, I need you to use delta I, and you got formula 2 that says, in order to calculate delta I need an L. So over on the right side, I've got a delta I that basically gives you a guesstimate on what your delta I will be, so that you can get an L and then calculate your delta I for the rest of the formulas, right? So usually I start out with the one on the right, drop down an L, and your L is always going to be some number. They don't make a lot of inductors out there, so you'll use your next size up, so you'll be fine, and then that you can calculate the real delta I. And that's why we got right there is that delta L estimate. That was the formula on the right. Based on that, I calculated out a 5.04 microhenry inductor. Of course, they don't make those, or if they do, they're expensive. Anyway, I always try to stick to standard ones because it's just an inductor anyway. So the next standard one up, you always want to go up, is 6.8 microhenries. So I went to use that one, and then using that 6.8 microhenries, I can then calculate the actual delta I. And with that, I can calculate the output capacitance and the I max out. With the I max out, this is important because this is what your inductor, when you actually size this inductor, you're going to want to pay attention to this value. This is your saturation current. You need the saturation current of your inductor greater than this maximum current. Because remember, we're not putting a constant current through this inductor. We're actually trying to have a huge current inrush into the inductor in order to charge it so that then we can charge the caps later. So our inrush current is always going to be greater than our average current, right? It's just that whole area under the curve, the derivatives and things like that. So always make sure that your saturation current of the inductor is at least what your I out max calculation is, but it should be greater. I usually like having 80% buffer, which means that whatever the amp rating on my inductor is, 80% of that rating will be this 5.35 amps. So now let's go ahead and run the simulation. Just some things I want to point out. You can see here, our calculator said 6.8 microhenry. I've got a 6.8 microhenry inductor, and it said C out of 171 microfarad. I just put a 220 mic cap on there as my output. Some other things to note when you're talking about that I out max, not only do you have to look out for the inductor, but whatever goes through that inductor goes through that FET. So just as the inductor needs a saturation current greater than 5.35 amps, based on these calculations, that MOSFET is also going to need a current rating greater than 5 amps in order to not blow up. And you're also going to want to pay attention to the RDS on that because that is 5 amps. So definitely be aware of the RDS on of the MOSFET there. So here you can see already just from this, we can see within 2 milliseconds, I'm actually able to produce pretty close to 12 volts out as expected. If I bring up the cursors and just move that over, you can see it's pretty much going to be like 11.4 volts or something like that, which is pretty close to 12. When we zoom into the current going through the inductor, it goes anywhere between 1.4 amps and 2 amps as the switching FET is switching. So let's take a look at the switching FET now. So here's the switching FET overlaid with the inductor current. And just as we expect, right? When gate on the switching FET is high, we're going to charge the inductor. When that gate goes low, the FET turns off, and then the inductor is going to go into discharge mode. So this is how the switching FET and the inductor relate to each other. So let's go ahead and see what our duty cycle is of the switching that we have going on right now. So we can see our switching frequency here is 500 kilohertz, just as we expected. And if we take a look at the T on of the gate, we can see it is 1.42 microseconds. And at 500 kilohertz, you're about a 2 microsecond period. So 1.42 divided by 2 microseconds gives us about a 71% duty cycle. So the question is does this circuit really work like a boost controller would? If this was a true boost controller that I was using, all I would have to do would be change the feedback resistors, and then that would change my output voltage. Because remember, that's your feedback, right? So if you want 6 volts, you just have to choose the right resistors to give you a feedback at 1.2 volts when V out is 6 volts. And so to do that, if I want to make this 6 volts instead of 12, then all I got to do is change this to 40K. And now my feedback is 1.2 volts at 6 volts. And now if I run it, I should have a 6 volt on the V out. So here you can see, all I did was change the feedback resistor. I went up above a little bit at the start before it started settling down. But once it's averaged out and leveled out, it gave 6 volts just like I wanted. So all I got to do is change the feedback resistor and it'll change my output voltage accordingly. Let's just do one more for fun, right? Like if I want 9 volts out, that means that I have to have 9 volts on V out and still get 1.2 volts at the feedback. That means that my R1, I just got to change that to 65K. And then rerun the simulation. So you can see, all I did was change the feedback resistor to give me 1.2 volts with a 9 volt output. And you can see that our output is really close to 9 volts. So that's all there really is to a boost circuit. Now I'm going to take this back down to a 6 volt output, because you notice that as I start getting higher, I start saturating everything, and I'm reaching probably 12 volts is getting close to the max of whatever components that I've put here and its functionality. And that's why we didn't see too much of a ripple at the 12 volt range. But the 6 volt range shows us a nice ripple, so we can go take a look at some of the other circuits. So let's go ahead and run this again with 6 volts output. Now I got my 6 volts out. And now you can kind of see what's happening with the voltage feedback and that V reference, right? So as the voltage feedback goes up and down, as the output voltage goes up and down, we kind of toggle around that V reference. And then as you would expect, as we're toggling around that V reference, as we go lower and come up, then our output is going to start turning on and off. Then as our output is turning on and off on that V comp out of the comparator, so now what we're going to do is we're going to zoom in a little bit to this guy right here. And then we're going to go ahead and take a look at our ramp signal. Remember, this thing's running at 500K. So let's take a look at it real fast. And then so we can see here, let's zoom in a little bit more, just to the part when it's on, right? That's what we want to care about. And so when we zoom in on that point, get rid of this reference, get rid of our feedback, because we're in like really tight right now. We just care about this comp and the ramp. And now if we look at our control signal, you can see that our control signal is only operating during the time that our comparator is high. So long as our comparator is high, then our ramp can then work to turn the MOSFET on and off, and that's where the switching frequency comes into play. So long as the comparator output of the feedback and the V reference is low, then the overall control is low. But so long as V comp is high, then the ramp is able to do some stuff and be able to actually turn the FET on and off, which gives us our output that we are looking for. So in short, that's the boost topology. I hope you enjoyed it. I hope you learned something. And like I said, just go out there. You don't have to use these comparators to make this thing work. If you want to, you can. You can try to breadboard this and make your own boost topology. But honestly, they make controllers out there. They're not that expensive. And there's a lot of filtering that I do not account for in this simulation, just using the two comparators, that those ICs take into account. So they work a little bit better. You can get things with PFM modes that are a little more efficient. And that's the big thing too, is you get the controllers, and depending on what you're trying to push, they can get up to like 92, 95% efficiency. They also have very low quiescent current. So there's a lot of benefits to just going with a controller rather than this. But if you want to try this out on a breadboard, just for fun, it the simulation works. So simulation doesn't lie. It will work at the end of the day. So just remember the main things on the boost circuit, the power components, is going to be that inductor, looking out for the saturation current. It's going to be that MOSFET. Make sure that it can also handle that peak current. Make sure that the MOSFET's RDS on is rated a good value. Like you don't want to use something with 2 ohms of resistance because that'll mess you up. And make sure your diode, your output diode, can handle the current that you want to push also, because if you're trying to push like this one's 1 amp, you're going to want a 1 amp diode in order to do what you need to do. Otherwise, the diode will blow up. Other than that, that's how you go from 3.6 volts up to 12 volts using some hardware. I hope you enjoyed it. If you did, be sure to leave a comment down below and let me know if you have any other ideas that you want me to go over, and I'll be happy to take a look at it. Other than that, until next time, have a good day.